Okay, so we're starting into this next topic called phase diagrams. And the best way to introduce phase diagrams is to ask this basic question. What causes water to boil? Okay, I'd be willing to bet that if you asked 100 people what causes water to boil, they would say something having to do with heat. Once you get it hot enough, it's going to go from being a liquid to being a gas. You're going to see little bubbles form at the bottom, which we normally think of as boiling. All right, and while it is true that heat has something to do with causing water to boil, that's only part of what makes it boil. All right, so part of what makes water boil is obviously temperature, but there's another factor that affects when water boils. And what is often overlooked is that the point at which water boils has both to do with its temperature and the pressure of the air that's around it. Okay, so what I've shown here is what's called a phase diagram. All right, specifically, this is a phase diagram for water. All right, and in the phase diagram, there's always going to be, it's always a graph that's got an x and a y axis. All right, on the x-axis is temperature, on the y-axis is pressure. What they're talking about there is the pressure on top of the liquid. So there is air pressure on top of this beaker pushing down on it, all right? And that is what is meant by this right here. So how much pressure is pushing down on this? Well, right now, since we're not doing anything to this container, you could assume that it's normal atmospheric pressure, all right? Which we generally consider to be about 1 atm, or 1 atmosphere, all right? And that's what we're going to represent by that little line right there. Okay, we posed the question earlier, what causes water to boil, right? So ask yourself, if I were to put this onto a stove and start heating it up, does that change the amount of pressure pushing down on it? Does the atmospheric pressure all of a sudden change because you start heating water on the stove? No, it's still going to be the same atmospheric pressure pushing down, okay? So if you are at atmospheric pressure and you start to increase the temperature, okay, what happens? Well, let's think about what happens to water when it's really cold, all right? When it's really cold, it's ice, all right? It's in its solid form, okay? So what happens as you start to let ice warm up, but keeping it at the same pressure, all right? This is essentially what happens to an ice cube if you just set it out for long enough. The same pressure is on top, but the temperature is increasing. It gets to a certain point, and what happens? It goes from solid to liquid, all right? And what's the name for that? Melting. All right? So let's say that we, instead of just warming it to room temperature, we keep on heating it up. All right, we're still not doing anything to the pressure. And then all of a sudden, we get to this point where it goes from the liquid part to the gas part. All right, what is that? Boiling. All right? So to get back to our earlier question, what causes water to boil? All right, does it have something to do with temperature? Yeah. What if we put this into reverse and then you let that cool? All right, it's going to go from its gas form back to its liquid form. All right, what do we call that? That is condensation. Okay, we let it cool and cool and cool and cool. It eventually is going to pass through room temperature, and let's say we cooled it down even more than that. All right, we put it in the freezer, for example. It's going to pass from its liquid form to its solid form. And what is the name for that process? That is freezing. Okay. But one thing about this that you might notice is that if you're not at 1 atmosphere of pressure, it's not necessarily true that water is going to undergo the same type of phase changes than it would if it was at 1 atmosphere of pressure, all right? And so if you look at this phase diagram for water, you probably notice that the normal phase changes that we're used to, melting, freezing, boiling, and condensation, aren't the only types of phase changes that can occur, all right? So specifically, what about this little line right here? All right. What if something were to go from here to here? All right. This is going from a solid form to a gaseous form. All right. Normally, we don't see that with most materials, but what I'm going to get to is that this is a possible type of phase change. And what is the name for this? Going directly from solid form to gaseous form, okay? There is a name for this. It's called sublimation, all right? And one of the most common types of materials that sublimes is carbon dioxide, all right? Dry ice. If you think about when you have dry ice, you have carbon dioxide in its solid form, and when it warms up enough, it goes straight from the solid form to the gas form, all right? And the name for that is sublimation, all right? So what about the other way? Deposition, okay? So we're going to talk about a little bit about these different phase changes, and hopefully make you think about materials in a little bit of a different way than you have before. Okay, and so here's a question that I want you to think about. Is it possible for water to go straight from its solid form to its gas form? All right. Normally, you don't think about that. We think of, okay, when water's in its solid form, it first has got to melt and be in its liquid form, which we commonly call water, before it eventually boils. All right. But what this phase diagram indicates is, well, what would happen if water were, say, at a point down here, and it were to go to a point over here? Well, it looks like it would go straight from being ice to being steam without ever going through liquid water, all right? And the thing is, this type of a transformation is entirely possible, all right? The reason it might seem weird is that we're used to thinking about water existing when it's under 1 atmosphere of pressure, all right? But you can manipulate conditions so that water is not under 1 atmosphere, and I'll show you a little demonstration right here. All right. As I was saying, we're used to thinking about materials as being under 1 atmosphere of pressure, all right? So I've got a little syringe here, and I've added a little bit of water to it, all right? And there's no cap on this syringe, so air is free to come in and out if it wants to, all right? Typically, why would air come in or out? Air is either going to travel in or out in order to equalize the pressure between the inside of this and the outside, all right? So if I put my thumb over the top here, and then I squeeze the bottom here, all right? If you go back to the gas laws, if you take a sample of air, and while the temperature is the same, if you decrease the volume, you should realize that the pressure is going to increase, all right? And so the pressure in the air above that liquid is now higher than 1 atmosphere, okay? Let's say that this right here is room temperature, all right? And, okay, so right now, where on this phase diagram is this water, okay? It's right about right there. It's at room temperature, and it's at 1 atmosphere of pressure, all right? So what am I going to do here? I'm going to put my thumb over the top, and I'm going to squeeze it, all right? And what that does is that increases the pressure over top of that liquid, okay? So where is the water in this now, according to this phase diagram, okay? I can feel it, there's no increase in the temperature. But what you've done is the water has now gone from room temperature to this point right here, where the only thing that's changed is that it's at a higher pressure, okay? So it was water before, it was water after. Why is that the case, all right? Because there's been no phase change, all right? It's gone from one section of liquid to another section, all right? The only time you would expect there to be a change in the phase would be if it crosses one of these lines, okay? So can this water be under a lower pressure? Certainly. Okay, we can take, all right, the water now is under atmospheric pressure, all right, we know that because this is not a sealed container. If I put my thumb over the top and I pull back on, the syringe, okay, we should expect that the pressure on top of the water now is at a lower pressure, all right? And you can demonstrate that because if I let go of this, you can see plunger wants to return to its normal shape, all right? So right now, when I pull back on that, you can assume that the air inside of that syringe on top of the water is now at a lower pressure, all right? So how would you show that in a phase diagram? All right, that would be a case where, let's say, this is normal water, room temperature, 1 atmosphere of pressure, all right? It's going to be going to a lower pressure, all right? And you notice that there wasn't a phase change, it was water before and water after. That's why when we go from here to here, we're still in the part of the phase diagram where you're liquid, all right? But something should strike you about this. What would happen if we lowered the pressure on top of that water to the point where it crossed this line, okay? All right? So if you were to, while keeping water at the same temperature, all right, room temperature, is it theoretically possible that you could get the pressure on top of it low enough that it would turn from the liquid state to the gas state? All right, and the answer is yes. I mean, it is possible, and there are a couple of video links that I've directed you to on Moodle that'll show this. All right, if you take regular water at room temperature and you decrease the pressure enough on top of it, you can actually cause it to boil. All right, not by heating it, but by changing the pressure. All right.